animated and to vent at the poles of the galaxy. Yes.
So you said you put the same amount of
Yes.
energy,
Yes.
also in the same spatial volume in
Yes,
the two cases?
yes, that's what we did as well. So we made all sorts of games. You do it in the same volume, or you do it in the same amount of mass, and things like that, and you get the results just because of the resolution effects, not because we are weighting energy differently. Right. So we have done. Yes, we are very far from the event horizon. So with these type of simulations, we can at best go to the scales, depending on obviously on the black hole mass, which are close to the Bondi radius or slightly sub-Bondi radius. So we are talking about the scales of 0.1 parsec to a parsec, again, depending on the size of the simulation. And that is the best that we can achieve now. We could push the resolution further, but the time step would just bring to a halt. So we couldn't evolve the simulation at the present moment without more clever algorithms. So I want to show you a more physically motivated example of exactly the same thing. So we have with this method repeated one of our simulations that we have done in the past, and this is a zoom-in simulation of a redshift 6 quasar. So it's a really massive halo of few times 10 to the 12 solar masses. We see the black hole at early cosmic time, and we let it grow. And in one case, we don't use this super Lagrangian refinement. In the other case, we use it, and we let the simulation evolve to redshift 6. When the black hole mass is a couple of times 10 to the 9, it's accreting at the Eddington. So we have a bright quasar, and this quasar should do a lot of damage to this host galaxy. And this has been really a standard law in many galaxy formation simulations. So if you now, this is the whole halo. You can see the hot gas here, which is in part hot because it's virialized, in part because of the AGN feedback. You can see the cold filaments coming in this halo, and then you can zoom into the central region here. So this is just a schematic to tell you what's happening. This is the central galaxy. So this is the cold gas that is sitting in a rotation-supported disk. Again, it's the same picture. The AGN feedback is venting out of the galaxy along the poles, and it's actually, the disk is still happily star-forming and rotationally supported, so we don't get a morphological transformation of the galaxies, even with the massive black hole powering a quasar. So this is really now intriguing. I don't think we have an answer to this at this point. So this would tell us that the morphological transformation of galaxies might happen in a slightly different or more subtle way than we thought before with these large-scale simulations. But these simulations are very expensive, so it will take a couple of years to work through this and understand what is happening. Another example is you can play a different game. You can say, I don't change the resolution of the simulations, I just change the physics I put in. And we have a lot of uncertainties which type of physics we can put in simulations for different type of systems we are trying to simulate. So this is from the work of Tiago Costa, my former PhD student, which is now an MPA fellow in Garching. And what he has done now with a different code, this is Ramses, he has done what we call on-the-fly radiative transfer simulations, where he had tried to explore different ways how you can drive outflows again from high redshift quasars. So in this field, there are different ways how people address this. There is something like canonical energy-driven outflow solutions, then there are momentum-driven outflow solutions, and a third scenario is something that is called radiation pressure-driven outflow solutions. People have worked on that intensely analytically, but there is that much that you can do with analytics when you have a messy objects like this. So what Tiago has done here, he has performed the simulation 3 times, one without AGN feedback, and if you focus on these top plots, you're just showing the temperature maps, you can see the gas is hot just because of virialization. Then what he has done, let's jump to the last panel, he has done the same simulations, but now assuming energy-driven outflow solutions, so just dumping a lot of thermal energy and making sure that gas doesn't cool. So we mimic this type of solution, and then you get these really massively hot, fast outflows out of the host of these quasars that is propagating into the IGN. But if you now change this and assume that the quasar is shining at some luminosity set by the mass accretion rated radiative efficiency, and you assume that you have some dust that is coupled with the gas with some metallicity, you can then try to see what a radiation pressure-driven outflow is. And you find a different thing. You still find hotter outflows than you had with just no feedback at all, but actually there is an order of magnitude difference here in the temperature structure of the gas. And that gives us an uncertainty in which actually feedback mechanism is operating and how it's operating in this system, which is still quite large. Another curious thing about these radiation pressure-driven outflow solutions is that they actually do a physically different thing than the energy-driven solutions. Energy-driven solutions are really good at expelling gas fast and making it hot and sending it into the IGM and perhaps preventing the galactic fountain effect, while the radiation pressure-driven outflows are slightly more subtle. The outflows are more multi-phase, but they also can puff up really very dense optically thick gas because radiation is obviously very good at coupling there with multi-scattering, and they would then, from a very dense compact core of a galaxy, they will produce something that is a slightly more diffuse, even though still quite compact. So let me now switch gears completely. What am I doing with time?
20 minutes.
Okay. So I want to tell you now about a different physics. So away from supermassive black holes for a moment. Some water. I want to tell you a little bit about the supernova feedback in dwarf galaxies. So the standard lower here has been really for many years that supernova feedback in low mass galaxies solves all our problems. So this has been a magic ingredient that has been always used to say that we can reproduce realistic properties of dwarfs once we have an efficient supernova feedback. So in a work with my former PhD student, Matthew Smith, what we have done, we have tried to compare as many different schemes how people actually put supernova feedback in simulations to see whether we get different results and what can this teach us about how this feedback operates. So these are all simulations of dwarfs in isolation, so there is no cosmological context. This is a simulation without supernova feedback, so you have catastrophic overcooling, clumping of gas, which becomes self-gravitating. Then we have simulations where we dump supernova purely thermally, or we just affect the kinetic energy of the gas rather than the thermal. And then we have some kind of interesting models, I won't go into details, which are called delayed cooling, where people have invoked in the past quite successfully to prevent this numerical overcooling and to say that the energy that the supernova delivers in the ISM should be stored for a while before the radiative cooling takes it away. Let's say in simple terms, that's what it's trying to do, trying to prevent numerical overcooling. And the final model, which is perhaps the most interesting, which here I label as mechanical, is the one where you're saying if I'm resolving the Zeldov-Taylor phase of supernova explosion, I just don't do anything, I just dump my energy that I have there. If I don't, I go back to high resolution simulations of individual supernovae exploding in small boxes, and I take into account the momentum boost which I lost because I didn't resolve the Zeldov-Taylor phase where this momentum boost happens. And that's an analytic prescription that you can put in your simulation, and for each supernova exploding you can check whether which spatial case you're resolving, and you can say, shall I be adding this momentum boost or not, based on these high resolution simulations. So what do we get from this? So this is again a resolution study plus the physics study. So we go from something like 2,000 solar masses to 20 solar masses. And you can see that the majority simulations at a kind of coarse resolution, but really this is not super coarse, it's actually quite okay. What do? They overproduce the number of stars formed in this dwarf galaxy. You really have to move to extremely high resolution to get the stellar mass content of these galaxies in shape and fine. So this is a really curious thing. Once you reach this extremely high resolution, all models start to converge to a single answer. And if you look at it also, it has a star formation rates as a function of time. All models, apart from this is no feedback case, it's not surprising. And this is this delayed cooling case, which I would suggest that it has some unphysical parameterizations to it, so it's not to be taken too seriously. They start to produce similar results. So there is some characteristic scales both in mass and spatial scales in times where we actually start to get rid of numerical cooling, overcooling in this simulation. So it means whatever, however your energy you start dumping it in, you start doing the right thing. And that is telling us that we really have to worry which physical scales we are resolving in simulations, how we are doing things. No. And the second thing, if you go back at this plot, you see that this mechanical feedback scheme seems to actually do quite okay job for all levels of resolution. So that means that this scheme is trying to cope with numerical overcooling at coarser resolutions better than the other schemes, so it's slightly more robust. However, that would be too nice to be true. If you look at the outflows from this galaxy, and this is now only with the mechanical feedback scheme, you can see while the star formation rates are largely converged, as I showed you before, the outflows are not. And this is now color-coded with the radial velocities, where red is going away from the disk, blue is coming towards the disk, and you can see at the coarser resolution, which is the top, you have a lot of fountain effect. You have a lot of gas that is falling back to the disk. When you crank up the resolution to these 20 solar masses, what you get is much more hot outflows, so you're starting to expel more gas out, your mass loadings go up. So what does this tell us when we try to do this in full cosmological simulation? So we have done this experiment simulating 5 different dwarfs in different environments, which is showing here. So some that are really in crowded regions like here, some that are close to a void. And what you can see at a glance what's happening in this is the dark matter distribution.